Every AI model you use today, ChatGPT, Gemini, Sora, DALL-E, was trained using one single algorithm, backpropagation. It is the engine behind all of modern AI. And in this video, you are going to understand it completely, from the very first principles, all the way to how PyTorch uses it to train billion parameter models. By the end of this video, you will never look at a neural network the same way again. Let us begin. So what does it mean for a neural network to learn? Learning is simply this: adjusting the weights inside the network to reduce the error it makes on predictions. There are 3 steps. First, the network makes a prediction, the forward pass. Second, we measure how wrong that prediction is, we call this the loss. Third, we adjust every weight to make the loss smaller, this is backpropagation. And we repeat these 3 steps thousands of times until the loss is tiny. The key question backprop answers is, by exactly how much should each weight change? The answer is the gradient, dl over dw. Before we can update weights, we need to measure how wrong we are. That is the job of the loss function. The loss gives us a single number, the higher it is, the worse our predictions. For regression, we use mean squared error, the average of squared differences between predicted and true values. For classification, we use cross-entropy loss. Think of the loss as a bowl-shaped surface. Our weights are a point on that surface. Our goal is to find the lowest point of the bowl. Backpropagation tells us which direction to step to get there. In the forward pass, data flows left to right through the network. Each neuron takes its inputs, multiplies them by weights, adds a bias, then passes the result through an activation function. The weighted sum z equals w times x plus b. Then the activation a equals sigma of z. This process repeats layer by layer until we get the final prediction. Here is the critical thing: during the forward pass, we save every intermediate value, every z in every AI. Backpropagation will need all of them when computing gradients. Think of the forward pass as recording a computation history. The gradient is the slope of the loss with respect to a weight. If the gradient is positive, increasing the weight increases the loss, so we should decrease the weight. If the gradient is negative, increasing the weight decreases the loss, so we should increase the weight. The weight update rule is W equals W minus the learning rate times dl over dw. We move in the opposite direction of the gradient, downhill on the loss surface. The learning rate controls how large each step is. Too large and we overshoot. Too small and we crawl. The gradient is the compass. The learning rate is the step size. Now we reach the heart of backpropagation, the chain rule. A neural network is a chain of composed functions. L depends on A, which depends on Z, which depends on W. The chain rule says, to get dl over dw, multiply all the local derivatives along the path. dl over dw equals dl over d, times d over dz, times dz over dw. Each term is cheap to compute at its own node. The key insight is that each layer only needs its own local derivative. It receives the gradient from the next layer, multiplies by its own local gradient, and passes the result further back. This is the entire algorithm. Let us work through a complete example with real numbers. We have input x equals 2, weight w equals 0.5, bias b equals 0, true label y equals 1, and sigmoid activation. Forward pass, z equals 0.5 times 2 equals 1.0. A equals sigmoid of 1 equals 0.731. Loss equals half of 0.731 minus 1 squared equals 0.036. Now backward, dl over d equals a minus y equals minus 0.269. d over dz equals a times 1 minus a equals 0.197. dz over dw equals x equals 2.0. Chain rule, dl over dw equals minus 0.269 times 0.197 times 2 equals minus 0.106. Weight update with learning rate 0.1, w becomes 0.5 minus 0.1 times minus 0.106 equals 0.511. The weight increased, correct direction. Let us now visualize how the backward pass actually flows through the graph. We have a chain of nodes, W, Z, A, loss. During the forward pass, values flow left to right. During the backward pass, gradients flow right to left. We start at the loss and compute dl over d. Then we pass it to the activation node, which multiplies by its local gradient d over dozen. Then further to the linear node, which multiplies by dz over dw. The critical efficiency, each gradient is computed exactly once. The gradient dl over d is computed at the loss node and reused by every node behind it. Without this reuse, the cost would be exponential in deep networks. This reuse is what makes backpropagation practical. In a multi-layer network, the same chain rule applies, just with more layers. We use the delta notation to make it clean. Delta at the output layer is dl over dz at that layer. For any earlier layer L, delta L equals W of layer L plus 1 transposed, times delta L plus 1, times the derivative of the activation at ZL. This is the chain rule in matrix form. The weight gradient for layer L is dl over dWL equals delta L times the activations of the previous layer transposed. Notice the shape, dl over dW always has the same shape as W itself. This makes the update rule clean. Every weight matrix is updated by subtracting the learning rate times its own gradient matrix. The choice of activation function directly determines how well gradients flow. The sigmoid function squashes everything between 0 and 1 and its gradient is at most 0.25. When you have 100 layers and multiply 100 gradients together, each less than 0.25, the result is astronomically small. This is the vanishing gradient problem. ReLU, by contrast, has a gradient of exactly 1 for all positive inputs and 0 for negative inputs. No shrinkage. Gradients pass through cleanly. This is why ReLU became the default activation for deep networks. For the output layer of a classifier, softmax is still standard. But for hidden layers, ReLU and its variants like leaky ReLU dominate. Vanishing gradients are not just a mathematical curiosity, they break training. With sigmoid activations, the gradient at the first layer of a 100-layer network is roughly 0.25 to the power of 100, essentially 0. The first layers receive no gradient signal and never learn anything useful. The exploding gradient problem is the opposite. Gradients multiply together and grow exponentially, leading to weight updates so large they cause NAN. The fixes for vanishing gradients are, use ReLU activations, add batch normalization between layers, and use skip connections like ResNet. The fix for exploding gradients is gradient clipping. We cap the gradient norm at a maximum value before the weight update. Plain gradient descent computes the gradient on the entire dataset before each update. This is accurate but extremely slow for large datasets. Stochastic gradient descent, or SGD, uses just one sample at a time, fast, but very noisy. Mini-batch gradient descent is the standard compromise, use 32 to 512 samples per update. You get the speed benefit of small batches and the stability of larger ones. Almost every AI model you have heard of, GPT, ResNet, BERT, was trained with mini-batch gradient descent. The batch size is a hyperparameter you tune. Common starting points are 32 or 128. Plain SGD treats every weight with the same learning rate. Momentum improves this by accumulating a velocity vector. The gradient is smoothed over time, reducing noise. RMSprop adapts the learning rate per weight based on recent gradient magnitudes. Weights that have been getting large gradients get a smaller learning rate. Atom combines both ideas, momentum for smoothing and RMSprop for adaptive scaling, plus a bias correction term for the first few steps. Atom with learning rate 0.001 and default beta values is the starting point for virtually every modern AI training run. It is the default optimizer in PyTorch and TensorFlow for good reason. Before backpropagation can do anything useful, the weights need to start at sensible values. This is weight initialization. If you initialize all weights to 0, every neuron computes the same gradient, a phenomenon called the symmetry problem, and the network never learns to specialize. If you use large random values, activations explode or vanish from the very first forward pass. Xavier initialization scales weights by the inverse square root of the number of inputs, designed for sigmoid and tan activations. Initialization, the default in PyTorch, scales by the square root of 2 over n, designed for ReLU. Starting with the right initialization can mean the difference between a network that trains in hours and one that never converges at all. Batch normalization is one of the most impactful techniques in modern deep learning. After each layer, before the activation, we normalize the outputs to have mean 0 and variance 1 across the mini-batch. Then we apply learnable scale and shift parameters, gamma and beta. These parameters are also updated by backpropagation. Batch norm solves the problem of internal covariate shift. As earlier layers update their weights, the distribution of inputs to later layers keeps changing, slowing training. By normalizing, we stabilize these distributions. The result, you can use much higher learning rates, train faster, and often need less dropout. Even with good gradients, networks can memorize the training data instead of generalizing. This is overfitting, and regularization is how we fight it. Dropout randomly zeroes out a fraction of neurons during each forward pass. The gradient of a dropped neuron is 0, it receives no update. Active neurons are scaled up by 1 divided by the keep probability. A different set of neurons is dropped each mini-batch, forcing the network to learn redundant representations. L2 regularization adds a penalty equal to lambda times the sum of squared weights to the loss function. This means backprop now also computes gradients to shrink weights toward 0, discouraging large values. Remember, always disable dropout at inference time with model.eval. PyTorch and other frameworks implement backpropagation automatically using a computation graph, also called autograd. During the forward pass, every operation records itself as a node in the graph, storing the local gradient function as grad_fn. When you call loss.backward, PyTorch traverses this graph in reverse, applying the chain rule at each node to accumulate gradients in the .grad attribute of every leaf tensor that has requires _grad equals true. This dynamic computation graph is rebuilt fresh for each forward pass, which is why PyTorch can handle variable length inputs and conditional logic naturally. The graph is freed after backward to save memory, unless you explicitly pass retain _graph equals true. The learning rate is perhaps the most important hyperparameter in training. Using a fixed learning rate throughout training is rarely optimal. Learning rate schedulers automatically adjust the learning rate during training. Step decay reduces the learning rate by a factor every few epochs, simple and effective. Cosine annealing smoothly reduces the learning rate following a cosine curve, reaching near 0 at the end of training and often cycling. Warm-up starts with a very small learning rate for the first few hundred steps, then ramps up to the target value, essential for transformer models which are sensitive to large updates early on. One-cycle learning rate policy is popular for training quickly and effectively. Recurrent neural networks process sequences by feeding the hidden state from one timestep into the next. To train an RNN with backpropagation, we unroll it across timesteps, creating a deep network where each layer corresponds to one timestep. This is backpropagation through time, or BPTT. The same weight matrix WH is used at every step, so its gradient is the sum of contributions from all timesteps. But unrolling creates a very deep graph, and gradients must be multiplied through all those steps. With TAN activations and long sequences, vanishing gradients become severe. LSTMs and GRUs solve this by adding a cell state that acts as a gradient highway, able to carry gradient signals across hundreds of timesteps without multiplication. Residual connections, introduced in ResNet in 2015, solved a fundamental problem. Why do very deep networks train worse than shallower ones, even with ReLU and batch norm? The answer was that gradients still degraded over many layers. The residual block adds a skip connection that bypasses the layers. The output is f of x plus x, rather than just f of x. When we backpropagate through this addition, the gradient of x has a term of 1 from the skip connection. No matter what happens in f, there is always a clean gradient path through the identity shortcut. This enabled training networks of 152 layers and beyond. Skip connections are now standard in virtually every modern architecture, including transformers, where they appear as the add and norm layers. You might wonder, does backpropagation work for transformers? Attention mechanisms, softmax, layer normalization, are all of these differentiable? Yes. Every operation in a transformer is differentiable. The self-attention formula is, attention equals softmax of Q times K transpose divided by square root of dk, times V. Softmax is differentiable. Matrix multiplication is differentiable. The chain rule applies to all of them. The query, key, and value weight matrices, WQ, WK, WV, are all leaf parameters updated by backpropagation. The skip connections in transformer blocks protect gradient flow, just as in ResNet. GPT-4, with its trillion parameters, is trained by applying this same backpropagation algorithm, just at an extraordinary scale. Even with ReLU and skip connections, gradients can sometimes explode, especially in RNNs and during early transformer training. The symptom is a sudden spike in the loss, followed by NaN values. Gradient clipping is the solution. After computing all gradients with loss.backward, but before the optimizer step, we measure the global gradient norm, the square root of the sum of all squared gradient values across all parameters. If this norm exceeds a threshold, typically 1 or 5, we scale all gradients down proportionally so the norm equals the threshold. This preserves the direction of the gradient while bounding its magnitude. In PyTorch, torch.nn.utils.clip_grad_norm_, passing the parameters and max norm. BERT, GPT, and most transformer papers use max norm of 1. Let us look at the complete PyTorch training loop. Every line maps to something we have covered. First, define the model and atom optimizer. Inside the training loop, call model of X for the forward pass. Compute the MSE loss. Call optimizer.0_grad. This is critical. PyTorch accumulates gradients by default. If you forget 0_grad, gradients from multiple batches add together and your updates become completely wrong. Call loss.backward. This runs the entire backward pass, computing dl/dw for every parameter via the chain rule. Optionally, clip gradients to prevent explosions. Finally, optimizer.step. This applies the atom update rule to every weight using the stored gradients. 5 lines. Predict, measure, 0, backprop, update. Debugging a broken training loop is a skill every deep learning engineer needs. The most common mistake is forgetting 0_grad. Gradients silently accumulate and your model behaves unpredictably. If you have a detached tensor in the computation graph, gradients stop flowing past that point, weights behind it never update. NaN loss usually means your learning rate is too large, your weights were poorly initialized, or gradients are exploding. Use gradient clipping and check the gradient norms per layer. If you use model.eval during training instead of model.train, batch normalization and dropout behave differently, a subtle bug that can silently hurt performance. The golden rule of debugging neural networks: overfit a single batch first. If your loss does not drop to near 0 on one batch, your gradient flow is broken. Fix that before adding any data. Let us write out the complete mathematics for a two-layer network. The network is y hat equals sigma 2 of W2 times sigma 1 of W1x plus B1 plus B2. The loss is L equals 1/2 of y hat minus y squared. For the output layer weight W2, dl/dw2 equals y hat minus y times sigma 2 prime of Z2 times A1. For the first layer weight W1, we apply the chain rule one more time, dl/dw1 equals y hat minus y times sigma 2 prime of Z2 times W2 times sigma 1 prime of Z1 times x. Notice the pattern, each additional layer adds one more multiplication to the chain. The bias gradient is simply delta, the same as dl/dz, because dz/db equals 1. In matrix form, delta L equals WL plus 1 transposed times delta L plus 1 times the activation derivative at ZL. This is the complete derivation. Let us recap all 27 concepts we covered. 1. Learning means reducing loss by adjusting weights. 2. Loss measures prediction error. 3. Gradient is the slope of loss. 4. Chain rule multiplies local derivatives. 5. Forward pass computes and stores activations. 6. Backward pass flows gradients right to left. 7. A single neuron needs 3 local gradients. 8. Multi-layer backprop uses delta notation. 9. Gradients are reused, that is the efficiency. 10 through 12, activation gradients and vanishing gradient. 13 through 15, exploding gradient, SGD variance, atom. 16 through 19, initialization, batch norm, dropout, autograd. 20 through 23, schedulers, BPTT, skip connections, transformers. 24 through 27, gradient clipping, PyTorch loop, debugging, maths. 1 algorithm. All of modern AI. You now understand backpropagation completely. From a single neuron to GPT-4, it is all the same algorithm. The chain rule, applied millions of times, to billions of parameters, across thousands of training steps. That is the engine behind every AI model that has changed the world. If this video helped you, please subscribe to Neural Monk for more videos in the Maths Behind AI playlist. Hit the like button, share it with someone learning AI, and leave your questions in the comments below. Next up, Gradient Descent Deep Dive. See you there.